Welcome to our next video in our discussion about discrete random variables and probability distributions. In this video, we're going to focus now on the mean and variance of a random variable, more specifically a discrete random variable. Okay, so first of all, the mean is a measure of the center of a probability distribution. Nothing fancy about that. We've already discussed what a mean is. It's just the average. So the mean is our average, or the center, of the probability distribution. The variance is a measure of the dispersion or the variability of a probability distribution, so how spread out it is. So the standard deviation then is another measure of the dispersion. It's the square root of the variance, and we'll get into standard deviations a lot more when we get into normal distributions, so give that a few sections or a few chapters. So the mean, or the expected value of a discrete random variable x, is denoted as mu. So this is one of our first Greek letters that we're going to see here in statistics, but this right here is the Greek letter mu. It's kind of like a curly U with a longer tail on the front. So we also call it E of x, or the expected value. So expected value is just another word for mean. So mu, which is equal to the expected value, is equal to the summation of each individual value of x times its corresponding y value, or each individual x value times its corresponding probability. So this mean then is the weighted average of the possible values of x, where the weights are the probabilities where the beam balances. It represents the center of the distribution. It's also called the arithmetic mean. So I want to talk about this for a second. A weighted average. So I don't know if any of you guys have taken statics yet, but in statics we find weighted averages for centroids all the time, right? So this then is just the weighted average where our beam, do you remember the analogy of our probability mass function being a beam? So this would be the average of where that beam balances. So the mean then may or may not be a given value of x. So if you think about the numbers 3 and 5, if I were to ask you what the average is of those numbers, the average would be 4, even though 4 isn't one of the numbers I'm asking you about, right? So the mean may or may not be an actual value that you're given. Okay, so if f of x is the probability mass function representing the loading on a long thin beam, then E of x is the fulcrum, you guys remember that word from physics, or point of balance. So this is kind of what I talked about on the previous slide, but if I have this right here as a probability mass function as a long beam, and all of these values then are probabilities that have different values, right? These are all at different points along my beam. Then this dot right here would represent the mean, okay? So then if I look at the same point over here, all of these probabilities right here are closer together, like their x values are closer together, but their mean is the exact same. That just means their weighted average is the same between these values and these values. So that just shows you an example of how we have that balance point on my beam. Okay, so now to find the variance. This formula is a little more ugly, and you have a few different options or ways to solve. So this time we're going to use sigma squared. So this is a new Greek letter. It's called sigma. It's like a circle with a line on the top. So sigma squared is the same thing as variance, or it stands for variance, or v of x. So I'm going to solve for variance, sigma squared, which is equal to v of x, by solving for the expected value of each individual random variable minus the mean quantity squared, which is the same thing as adding up the difference between each x value and the average, and then squaring it, and then adding them all up, times my probability. Or another way to look at it is adding up each x squared value times its probability and then subtracting off the average. So in my personal preference, I like this formula best right here. I think it's most straightforward to be able to understand the variance then is the difference between each x value and the average, and then I square that and times it by each respective probability. But you can use whatever one of these you want to use. Okay, so the variance then is the measure of dispersion or scatter in the possible values for x. So it's the average of the squared deviations from the distribution of the mean. Okay, so variance describes how far apart values are from each other. So if I use this exact same example I did a few minutes ago, this distribution right here has a larger variance than this distribution right here. So do you see that? We're kind of comparing each value, how far away it is from the mean. So like that distance and that distance and that distance. Overall, these values are more spread out than these values are. See how these are kind of clumped or clustered together? So this one has a bigger variance, or they're wider or more spread apart than this one. Okay, so let's look at an example on how to calculate this. The number of messages sent per hour over a computer network has the following distribution. Find the mean and standard deviation of the number of messages sent per hour. Okay, so if I have the number of messages per hour, so 10, 11, 12, 13, 14, and 15, then we have these probabilities that I'm going to get that many messages over this computer network. So I have an 8% chance that I'll get 10 messages, 15% chance I'll get 11, etc. So if you notice, this is a lowercase f of x, so this is a probability distribution, not a cumulative distribution. So based on all of this, I want to find the mean and the standard deviation. So if you remember the definition, the standard deviation is the square root of the variance. So really I need to find my variance first. Okay, so I just set this up in Excel. You can do it in MATLAB or by hand, whatever you feel most comfortable with. So I'm going to say I want to take x times f of x. So I'm just going to take this column times this column to get this, right? And then I'm going to do that for each row. So 11 times 0.5 is 1.65. 12 times 0.3 is 3.6. And you get the idea. Then I'm going to add all of those values up, and that gives me my average. So my average, or my mean, or my expected value, same thing. So I wrote equals e of x. That then is 12.5. So that's my expected value. Not too hard when you do it in a computer program, right? If you do it by hand, it's just a little more tedious, takes a little more time. On a test, obviously you'd have to do it by hand, but in that case you'd be given less values, so you wouldn't have to do it all. So if you remember, this right here is part of the formula to calculate my variance. So let's look at that really quick. So here I have the summation of x squared times f of x. So that's what I'm calculating. So that's going to be the summation of each of those, and then subtracting off mu squared at the very end. So the reason I chose this one right now, even though I told you before it wasn't my favorite, is because this is probably the easiest one to do on the computer. Okay? So I'm going to square each x value, and then I'm going to multiply it by f of x, and then that will give me 8. Okay? So same thing, 11 squared times 0.15 is 18.5. So I'm going to do that for each row, and then I'm going to total all of those up, and that will give me 158.1. Okay, so I know that my mean, or my expected value, is 12.5, and my variance then is 158.10, which I calculated down here near the bottom of the screen. Then I subtract off my mean squared, which is 12.5 squared. Okay, so that gives me then a variance of 1.85. But I still have to take the square root of my variance to calculate my standard deviation. So that then equals 1.36. So this stuff isn't really hard. That's how all of statistics is, right? It's not really hard. It's just being able to comprehend these new topics little by little as they come up. Okay, so then let's move on to calculating the mean and the variance of a function, not just a value. So if x is a discrete random variable with a probability mass function f of x, then I'm going to come into here and say the expected value of that whole function is the same thing as the x value times the function value. So notice I'm saying e of that value, so that value times the function value, all summed together. So if that function equals this, so the difference between the random variable and the average squared, then its expectation is the variance, meaning its expected value is the variance. So if that happens to be the case, then the mean and the variance are the same. So that won't always be the case, but if so, that's great. Okay, so let's look at an example for that. There's a chance that a bit transmitted through a digital transmission channel is an error. X is the number of bits received in error of the next 4 transmitted. What is the expected value of the square of the number of bits in error? Okay, so this looks like a similar setup to our previous example. However, the difference now is in the way it asks this question. What is the expected value of the square of the number of bits in error? So if you remember this formula we had on the previous slide, I have e of h of x, right? So I'm going to evaluate my function at something new. So in our case, we're going to be evaluating the function at x squared. So what is the expected value of the square of the number? So this is like way back in algebra when we evaluate our function at something. I'm going to now evaluate it at x squared. So that is going to be equal to the summation of x squared times f of x. Okay? So I do that in Excel and I say x squared times f of x. So I'm going to square each value and multiply it by its corresponding f of x. I do that for each row and I sum all of those up and I get 0.52. So that then is my expected value of x squared, or my mean of the square of the number of bits in error. Okay, so that's it then for mean and variance of a discrete random variable.